Good day, everyone. We are Modula and Podrick.
Let's dig into what is going on in tech and science news.
So, we hear about it all the time, right? This massive race to build a quantum computer. Companies are pouring billions into creating bigger and better hardware. But what if that's not the real problem? In this explainer, we're going to dig into the biggest bottleneck in quantum computing, and I'll give you a hint. The answer isn't in the machine itself. Now, that is a pretty provocative statement. It just cuts right through all the hype, doesn't it? It suggests that even if we had the perfect machine, right now we're missing a key ingredient. And honestly, this exact concern is the reason I left the entire field of quantum computing. Yeah, this one's personal for me. See, back in 2020, I finished my PhD in quantum computing at Cambridge. And while I loved the work, I just couldn't shake this nagging doubt. Would these incredible machines ever actually be useful? So I left. Now, 5 years later, I'm taking another look to see what's changed. So let me just set the stage for you. In 2020, the absolute best quantum computers had something like 50 qubits. But my real worry wasn't the hardware, it was the software. It felt like we hadn't seen any really new, useful algorithms since the 90s. Now, fast forward 5 years, and well, the hardware has absolutely exploded. The software story, though, it's a little more complicated. Okay, first things first, and this is crucial. Quantum computers are not just super fast versions of your laptop. You're not going to be playing video games faster on them. They are highly, highly specialized tools built for very specific kinds of problems. And to see why, we need to understand their fundamental power and their fundamental catch. So here's the magic. A regular computer, you give it one input, it gives you one output. Simple. A quantum computer, though, it can take every single possible input and process them all at the exact same time. This creates what you can think of as an answer cloud, a superposition that holds all the possible outputs, all at once. It's miraculous, right? But, and this is a huge but, the second you try to look at the answer, the entire cloud collapses, and it just gives you one of those answers completely at random. Poof! All that incredible computation just vanishes. Which, brings us to the billion-dollar question. If you just get a random answer back, what's the point? How on earth do you get anything useful out of that amazing answer cloud? The solution is all in the software. You have to run a very special kind of program, a quantum algorithm, before you take that measurement. This algorithm doesn't add more power. Instead, it cleverly nudges and manipulates that answer cloud so that when it collapses, the correct answer is way, way more likely to pop out. Designing these incredibly clever algorithms, well, that's the entire game, and it's exactly where the real bottleneck is. And that brings us to the central tension of this whole story. You see, while the people building the machines, the hardware folks, have been making just incredible progress, the people designing the programs to run on those machines, well, they've kind of hit a wall. It really is a tale of two very different development tracks. I mean, the contrast on this slide really tells you everything you need to know. On the hardware side, it's a rocket ship. Qubit counts are up tenfold in just 5 years. Companies are hitting their roadmap targets. But look at the software side. It looks stagnant. We are still mostly using algorithms that were discovered back in the 90s, with very few real-world breakthroughs since. We're building a supercar, but we don't have any new maps to tell it where to go. So where does this software gap hurt the most? Well, let's take a look at two of the biggest promises that were made about quantum computing, AI and chemistry, and see how this lack of new algorithms has led to a major reality check. All right, first up, quantum machine learning, or QML. The hype was all about these supercharged AIs. But here's the thing, quantum computers get their insane power from exploiting deep mathematical structure in a problem. But most machine learning today, it's about finding patterns in messy, unstructured, chaotic data scraped from the internet. It's just not a good fit for what quantum computers are designed to do. And because of that, a lot of the initial excitement around QML has really died down. The other huge hope was quantum chemistry. The dream was to simulate molecules perfectly, to design new drugs and new materials. And a key task here is finding a molecule's ground state. That's its lowest possible energy level. If you know that, you know how it's going to behave. And hey, we even have a quantum algorithm called phase estimation that seems absolutely perfect for this job. But then you run into this just devastating catch-22. To run the algorithm that finds a molecule's ground state energy, you first need to give it a really good description of what that ground state already looks like. You basically have to know the answer before you're allowed to ask the question. For discovering new molecules or new drugs, this isn't just a roadblock, it's a complete dead end. And look, this isn't just my opinion. A big paper in 2022 from leading scientists in both quantum computing and chemistry put it pretty bluntly. As you can see right here, they concluded that the evidence for a massive, game-changing advantage in chemistry, well, it just hasn't been found yet. That's a really sobering thought, coming from the very people we hoped would prove the opposite. Okay, so after all that doom and gloom, you might be feeling a little pessimistic. But it is not all bad news. Let's pivot now to the area where there is genuine, tangible, incredible hope. In fact, it's the very application that inspired the whole idea of a quantum computer in the first place: quantum simulation. The idea is just brilliantly simple. You see, trying to simulate complex quantum systems, like, say, the electrons buzzing around in a new material, is incredibly difficult for our normal classical computers. So, why not use a quantum system you can control, a quantum computer, to simulate a quantum system you can't? It's using quantum to understand quantum. It's almost too perfect. And the potential applications here are just staggering. We're talking about designing materials for room temperature superconductors that could revolutionize our entire energy grid, or simulating brand new materials for solar cells that completely blow past silicon's limits. We could even find a better way to create fertilizer, which is a process that currently consumes a massive chunk of the world's energy. This is the killer app. So this brings us right back to our central theme. We can see a clear path forward for the hardware, and we have at least one killer app in quantum simulation. But to unlock the full potential, we desperately need more tools in our software toolkit. We need more algorithms. And there is some good news on that front. In 2023, a new theoretical quantum algorithm was actually discovered, the first major one in a long time. This is huge because it proves that there are more algorithms out there, just waiting to be found. The bad news? This particular one isn't practical, at least not yet, but it's a sign of life in a field that desperately needed one. So what's the big takeaway here? It really seems like we've misallocated our resources. We have poured immense effort, time, and money into the monumental challenge of building the hardware. But, as this quote suggests, the search for the actual programs, the algorithms to run on that hardware, has been neglected. It's a brutally difficult field to work in, but as we've seen, it is arguably the most important one. So we end with this thought. The hardware is coming. Those incredible engineering challenges are being solved piece by piece. But the ultimate value of these revolutionary machines? That's going to depend on the answer to a much simpler question. What will we run on them? The race to build a quantum computer is well underway, but the race to figure out how to program it, that has only just begun.